Okay, folks, I'm hoping that you can hear me okay. This is the missed lecture. I'm sorry I couldn't give the lecture this morning. I had to go to a Department of Energy grant review thing where I had to give a talk at this grant review, so I had to do that. Okay, so let's continue our discussion of time-dependent perturbation theory. And today, what we're going to talk about is we're going to talk about sinusoidal perturbation, meaning one that goes as sine omega t, which is important for light. And we're also going to do Fermi's golden rule. Okay, so these are the topics. And so let's just remind ourselves what we did last time, and then we'll continue from that point. And so last time what we did was we were talking about what happens when we have a system like a box, and we have a bunch of states, the unperturbed states, and we're initially sitting in some state, we'll call it the kth state, and then we want to know what happens when we hit that with a perturbation h prime, and then we want to know what the transition is to some arbitrary mth state. And so then we want to know, suppose what we did last time was we said suppose that h looked like this, where it's 0 and then it turns on. This is a function of time t prime, and this is t prime equals 0, and then we're talking about what happens at some t prime equals t. Then if where this is constant, and so if we turn on that perturbation, we want to know what happens. Well, the starting point is to assume that our wave function can look like a sum over all the unperturbed states, and they all have their standard unperturbed energy phase factor. But now, because of the time-dependent perturbation, we put a little Cn of t in front, and that's the important factor, because then the probability to be in the nth state at some time t is equal to the amplitude squared of that factor. And so the question then becomes how to calculate that factor. And we know from our treatment that if we pick some Cn of t or Cm, doesn't matter what the index is, we calculated that that factor can be calculated. Whoops. Let's get rid of the. We calculated that Cm of t, the amplitude to be in the m state at time t is 1 over IH bar, integral from 0 to t of the perturbation, which is a function of time, e to negative I, ek minus em t prime over h bar dt prime. Okay, we just have to do that integral. Let's get this looking a little better. H bar. Okay, and so then we see that if this is what our h prime looks like, a constant, except it's just turned on and off, then we did the integral and we saw that the probability to be in state m at time t squared is equal to 4 times the absolute magnitude of the matrix element connecting the initial and final state times sine squared ek minus em times t over 2h bar divided by ek minus em squared. Okay, and so that was the result that we got. This is kind of all bumping into each other. And so then if we plot that, then we see that it oscillates in time. If we plot it as a function of time, then we see that it starts at 0, but then goes up and down and up and down. And the frequency, and so you can see that you can see what the frequency is. The frequency is going to be omega is equal to ek minus em over 2h bar. And then and then we did the and then we plotted it a different way. Cm of t squared, and we plotted it as a function of E sub m, the final state energy, where this then is the initial state energy, and then we see that the function now looks like this. And there's something, so we're just plotting this function, and so we see that that it's bigger. You can see that it's bigger when the final state energy is getting closer and closer to the initial state energy. That's the final state. This is the initial state. So it really likes transitions to degenerate states. You can see that from this plot. And something to notice that I didn't mention last time is this width changes in time. This width gets narrower as 1 over t. So as time goes on, it gets narrower in time. And the top gets bigger as a function of time squared. It goes as t squared. Let me write it like this. It gets bigger as t squared. And you can just see that from the function just by looking at it, because if I look at this function, then I can see that it goes as I can think of that as sine squared k. If I just do it like this, sine squared kx over x squared, then the limit as x goes to 0 is going to be, that's going to be on top, it'll be kx squared, and on bottom it'll be x squared, and so that's going to be k squared. And so here I would say that k x is equal to this ek minus em, and k is going to be equal to the t over 2h bar. And so then we can see that the limiting value is going to go as you can see that it's going as t squared over 4h bar squared. All right, so that shows you how it gets taller, but the narrower in time part comes from the fact that we see that function, this function, I have a sine function there, and so the first 0 is when of that function is when the first 0 of that function is when ek minus em t over 2h bar equals pi, right? Because sine of pi is 0. And so then we can see that that's going to be when ek, or I could say ek minus em is equal to 2h bar pi over t. And so I can see that this absolute value of this equals absolute value of that. And so then I can see that the first minimum will be when em minus ek goes as 1 over t, because that's 1 over t. And so that explains why it gets narrower in time. So there is this narrowing in time, and it gets taller. And so that kind of makes sense, because the thing is that I have all these levels, and I'm starting in some state k, and I'm going to some state, some arbitrary mth state. And you know that if the h prime goes like this, turns on and off, turns on at 0 and turns off at some t, then you know that for short times, then what happens is that you have a wide range of energies. Then you can couple to all the different energies, whereas for longer times, then they average out. Because the thing is that this guy has a phasor that's rotating with the energy ek, and this guy has a phasor that's rotating with the energy em, and so there's going to be the amplitude that's being sprayed back and forth. That green goo analogy I was making, when you have the amplitude going in each direction, there's going to be this phase factor e to the I em minus ek times t, because they're going to, both phase factors get multiplied. And so you can see that this thing is spinning. It's spinning. And so for a short time, then the oscillations don't average to 0. Oscillations don't average out. But for longer times, the oscillations average out. And so that's why for short times, you get some of the green goo sprays out, and you have a transition probability. But as you go longer times, then it starts oscillating back and forth, and the average starts tending towards 0. And so it's a funny little behavior there. And you can think about that. So, okay, but now what we're going to do is we're going to ask ourselves, now we're going to ask ourselves, what happens if the perturbation is sinusoidal in time? H prime is proportional to sine omega t. So this is a different case, and this is really important, because this is the case that is relevant to light. So this is the one that I think is most important. And so now it's relevant to light, because we know that for light, we have H prime is equal to E times E naught dot R sine omega t. And so if and so if we have so let's suppose that E naught is parallel to x hat, and so then we have H prime of t is equal to E naught x sine omega t. Okay, so that's the Hamiltonian, that's the perturbation for light. And so if I then have some atom or box, and I'm sitting here in the kth state, and if somebody shines a laser on me, then this is what's gonna, then I can ask the question, what's the probability that I go to some arbitrary state M? And that state could be higher in energy or lower in energy, it doesn't matter. And so this is the case we're talking about, where now this then is the Hamiltonian that is associated with this process. So you can see it's a sinusoidal Hamiltonian because of the sinusoidal nature of light, which I've mentioned before. Okay, so then we have to assume that we're initially in some state phi sub k, and we want to know the transition probability to state phi sub m. And so then we know that the probability to be in that nth state at some time t later is just going to be the magnitude squared of that of c sub m of t, that thing that the amplitude to be in the nth state. And we know what that amplitude is because we know the formula for it. It's just going to be this expression 1 over I h bar times the integral from 0 to t of h prime mk times sine omega t prime times e to the negative I ek minus em t prime over h bar. So this is just the accumulated amplitude because we know that it's spraying from the initial state into the final state, but there's some oscillations. These are the oscillations come from the difference in the phase factors. So the spray goes one way, then it goes the other way. But now that oscillation is also getting multiplied by the Hamiltonian. Give us some more oscillations. And so now you just have lots of oscillations, more oscillations. And so the question is, as we average over time, take that integral, what is the average of the amplitude that makes it to the final state after some time t? Basically, how much green goo ends up in that final state after we average all that spraying. And so we just have to do this integral. And so let's just do it. And let's remind ourselves that this matrix element is going to be equal to this phi sub m. I have to put the time independent part here, h prime of r, that's the part without the time, phi sub k. For this part is e, see this is going to be h prime of r sine omega t. And so this h prime of r for light is going to be e times e naught x, which is the same as e naught dot r. Okay, and so we got to do that integral. So let's do it. And so that integral, when we do that integral, it's going to be, so we're just going to do this integral, but to do that integral, we're going to do a trick. We're going to take the sine function. So we're going to do a little trick, and we're going to take the sine function, and we're going to just say we're going to break it up. Sine omega t prime is equal to 1 over 2i times e to the I omega t prime minus e to the minus I omega t prime. Okay, and so that's a little trick we're going to do. And so now when we write that integral again, I can write it purely in terms of exponentials. And there's a reason for doing that, because it just makes the integral easier. Because integrals of exponentials are always easier than integrals of trig functions. We all know that. And so this is equal to 1 over 2i times the integral from 0 to t h prime mk 1 over 2i times e to the I omega t prime e to the minus I omega t prime. times e to the negative I ek minus em t prime h bar t prime. All right, so that's the thing, and so those are, we see that there's all these oscillations are there, and so now we just have to do this integral, and so we can then write this basically as two integrals. What I can do is first I can notice that this part comes out because it has no time dependence, and so I can write this as 1 over 2i sorry, it looks like I'm missing the factor. Yeah, this is where I made my mistake. This is 1 over IH bar. And so 1 over IH bar. And so this becomes negative 1 over 2H bar times H prime MK 0 to T e to the negative I EK minus EM minus H bar omega T prime over H bar minus e to the negative I. I'm just multiplying these factors out. There's nothing special here. Minus EM. Now it's plus H bar omega e to the I omega. Okay, this is T prime over H bar. Okay, and this is dt prime. And so now I have these two integrals. And so what I can, so now let's do them. I can do these two integrals because they're just exponentials, and so the integrals are pretty easy. And so when I do the integrals, I get this. I'll just skip a line of algebra, and I'm going to get 1 over 2i h prime mk, and I'm going to get these two factors inside of here, one of which is e to the minus I ek minus em minus h bar omega times t over h bar minus 1 all over that same prefactor ek minus em minus h bar omega minus now the second term, which is going to be e to the minus I ek minus em plus h bar omega times t over h bar minus 1 all over ek minus em plus h bar omega. All right, and so okay, so now there's something really cool to notice. I got these two cases, but there's something interesting to notice, which is that first we remember that h bar omega is always greater than 0 because the frequency of the light is always a real frequency. So we're always assuming that frequency is just a real number. It's just, I mean, it's just a positive number. And so then what we see is that this leads to two cases, because the situation is going to be different depending on whether we got these two different cases. I'll write them out right here. So in the first case, I have all these lines, all these states. I'm starting out in the kth state. I have all these lines, all these states, starting out in the kth state. But in the first example, the final state EM goes up, is higher in energy. So I'll say here that EM is greater than EK, and we call that that's absorption. We'll call that stimulated absorption, stimulated absorption. And this other one is when EM is down. And so now I have EM is less than EK, and this one we call stimulated emission. So these are the two cases, and I'll call this one case 1, and I'll call this one case 2. And so let's treat these two cases separately. So we'll treat case 1 first. So this first one is when EM is greater than EK. And so we see then that what's happening here is when I look, now this is the really cute thing, if I look at these two terms, and I'll call this term A and this term B, then we notice that for this case, then we notice that term B is much bigger than term, well, it all depends on the details, but we'll just say it's bigger than term A. And you can just see that from the denominator, because you see that in this case, EK minus EM is less than 0. And so because that number is negative, we see that in term B, we have then a negative number plus a positive number. And so the denominator is smaller. Whereas in term A, we have here a negative number plus another negative number. And so that one is bigger, the denominator. And so, so we say that the denominator is smaller in B. And so that means then that we get to ignore A. And so then what we say is we only use then the B. And so what we have then is that Cm of T, for this case, when the final state is higher in energy than the initial state, then we say that the amplitude to be in that state at times T is -1 over 2I H prime MK to the -I E K minus EM plus H bar omega times T over H bar all over that same factor EK minus EM plus H bar omega and up here we have a -1. Okay, so that's what it's equal to, because that's just that's just what we get from the second term. So I'll say this is the second term. It's equal to B. And I should put wigglies here because it's an approximation. But then what we have is we have to evaluate this. And so we're going to do a little trick, just a little math trick. And so we're gonna pull a factor out of the numerator, and this is the factor that we're gonna pull out. Well, this factor will be the same. but the factor that we pull out is this. And it's not obvious why we should do this from the get-go. It's just a math trick, but let's do it and see where it leads us. Plus h bar omega times t over 2h bar. And then this is e to the negative I ek minus em. It's basically what we pulled out is half of that, of this part, h bar omega times t over 2h bar. But now I have from the other one minus e to the plus I times ek minus em plus h bar omega t over 2h bar. And that's all on top of ek minus em plus h bar omega. Okay, so that does not look simpler at first. It's kind of a complicated little expression, but it will become simpler. You'll very quickly appreciate why we did this, because what we notice is that I have this is equal to negative 1 over 2I h prime mk e to negative I k minus em plus h bar omega t over 2h bar times, now this is the trick, we look inside of this, inside of there, and we notice that that's actually a sine function. Yay! So we notice that what we have is a sine function. It's going to be actually it's going to be 2i. Let me just get all the signs right. It's cosine plus I sine. So it's going to be it'll be negative 2i sine of ek minus em plus h bar omega t over 2h bar divided by ek minus em plus h bar omega. Okay, so we just, because what was inside of there turned into a sine function. And so that was the cute little trick. And the cute little trick is not over yet, because what we do, because now we can see that, you know, these guys cancel. And then what we can do is, you can notice that now we're going to take this, the mod square of this to get the probability. And you can see that this thing goes to 1. When I take the mod squared of this thing, then the mod squared is 1. And so it's really quite nice, because then everything simplifies and we see that the CM of t gives me, when I take that whole thing squared, then I see that I get this nice expression, which is just h prime m of k magnitude squared, the matrix element that connects the initial and final state squared, times this familiar function sine squared times this energy difference between the final and the initial state, minus h bar omega, which is that the frequency of the light, times t over 2h bar all over that same energy factor. Okay, let me just make sure I got everything right. Em, what is the, okay, ek minus em plus h, right? Yeah, negative. Okay, yeah, em minus Okay, so I just took a negative sign there, but it all works out. Okay, so this is the right expression. And so this then is the probability to be in this state. Because what we've done is we've shown that this is the probability to have a transition from your kth state up to your mth state. And so this is absorption. And so this is basically the probability. You can think of this as the probability to absorb a photon. That's really what we've calculated. Because it's the electromagnetic wave at frequency h bar omega, and that electromagnetic wave is a photon. And so this is the probability that we will absorb energy from that electromagnetic wave and go to a higher state. So that's absorption of a photon. Although, let's just be clear that our theory, there's no photon quantization in our theory. At this level, there is no photon quantization. To get photon quantization, you have to do higher level theory. You have to do quantum electrodynamics, field theory, which we're not doing. But it's nice that we actually get the same answer that you would get from field theory. So it's really a cute result. And so this is the probability to absorb a photon and to go up into a state and have this transition. And so now what we do is, it's interesting to notice, well, there's several things to notice, but before we do anything, let's just look at the second case, case 2, which is the stimulated emission. So we did the stimulated absorption, and now let's do the stimulated emission. So for the second case, the final state is below the initial state. So let's consider case 2, where the EM is less than EK. So this is the final state, and this is the initial. And this is the emission of a photon. And so now, then we see that of these two terms, using that same reasoning as before, we see these two terms, but now the denominator is going to be bigger in B. And so this is the smaller denominator right here, because EK minus EM is now, EK minus EM is now a positive number. And so now the denominator in A is bigger. So everything is reversed. So now the denominator, so now the denominator is smaller in A. Denominator is smaller in A. And so the contribution of A is bigger than the contribution of B. And so then in this case, we can ignore the second term B for this time. So remember that my amplitude was these two parts, A plus B. So now we're ignoring the second one, B. And so that means then that we have Cm of T for this case, which is the stimulated emission. It's the emission scenario. And for here, we then have that the amplitude is a function of times be 1 over 2I times H prime MK times E to the negative I EK minus EM minus H bar omega T over H bar minus 1 to divided by EK minus EM minus H bar omega. And so it looks, the math is really just the same. So we just do the same math, do the same math trick as before. And so then we're going to end up with the really almost exactly the same answer. Cm of t squared, when we calculate it, is going to equal the matrix element squared times sine squared of EK minus EM minus H bar omega over 2H bar divided by EK minus EM minus H bar omega squared. And so this then becomes the probability to emit a photon, probability to emit a photon. And the thing to notice is that actually these two expressions are the same. The probability to absorb a photon and the probability to emit a photon are essentially the same expressions. So these two expressions are really the same. And so if we just do it like this, that's right. If we write it like this, let's let delta E be the energy difference between the initial and final states, but the absolute magnitude of that energy difference. So let's not worry about which one is on top and bottom. Let's just worry about that energy difference. And so that's going to be EK minus EM, but the absolute magnitude. And if we make that assumption, then we can see that the probability of either stimulated emission or stimulated absorption into some final state is going to be, that's delta E away, it's going to be this. We have the matrix element connecting the two states. And then we have sine squared. And now it's going to be delta E minus H bar omega times T over 2H bar divided by delta E minus H bar omega squared. Okay, so this is the final result. And that is the probability to have a transition when you shine light on something. So this is like a big result. Probability for stimulated emission or absorption. It's the same probability. And of course, we can plot this function. We can plot it the same as we did before. We can plot it as a function of time, in which case we see that it's a sine squared function. Just like before, we see that it oscillates. But now the frequency of oscillation is equal to delta E minus H bar omega divided by H bar. So that becomes the frequency. Okay, and then we also notice that we have that same behavior where if we look at the probability to have a transition to other energies as a function of energy, we see that as our final state energy goes away from our initial state energy, then we get a reduction in the probability. But now because of the structure of that function, it's not just It's not just the, it's the energy difference. If we plot the probability of a transition as a function of the energy difference between the two levels, then we'll see that the maximum probability is when the energy difference, delta E, is equal to, and you guessed it, h bar omega. So let's plot the function as a function. Let's plot the probability Cm of t squared as a function of the energy difference between the two levels, but we're 0 is h bar omega, and then you get this behavior, and that makes sense. We're just plotting this function, so there's nothing fancy here. We're just plotting this function, and that's what it looks like. And we have the same behavior. We see that it gets narrower as a function of 1 over time, and this part rises as t squared for the same reasons as before, because it has the same functional behavior as that last expression that we derived. Okay, and so this is important, because this is telling us, this is really this will give us, this is how lasers work, because in lasers, what's going to happen is you will have the laser medium, you'll have atoms where you get the electrons to go up and down, up and down, up and down in a correlated way. They go up and down, and that's what creates the laser, is because the light is in the laser, and that light is causing the atoms to just go up and down and up and down, and emit more and more, all in phase. And so this leads to laser behavior. And you can look that up to understand better. Okay, and so now what we want to do is we want to what we're going to do now is we want to ask ourselves what happens okay, so now what we're going to do is we're going to ask ourselves what happens when we're going to ask a different question. It's a very similar question, but we're going to say, what if this frequency was bigger than the absolute magnitude of the initial state, and you'll soon see why this is significant. Because what we're doing is, this is the picture that I've been drawing for you over and over, is that we have some box or atom, because an atom is like a box, and we're sitting here in the kth state. And so that means that this EK is a negative number, because it's a bound state. It's a bound state, so EK is a negative number. So that means that if I absorb the energy h bar omega, then you see that then I'll go up to this level somewhere here, and this level here is 0, the vacuum level. We'll call that vacuum level. The vacuum level is equals 0. That's just what we call it. And so now we see that if h bar omega is bigger than the absolute magnitude of E of k, then that leads to ionization. Hold on one second. Gory? Okay, I'm actually doing my lecture right now, so I can't talk. Okay, bye-bye. And so, so if I'm here and if I have this condition, then you see it takes me out, and so I get ionization. And that's a really important process, the ionization. And so that's what we want to talk about now. And so this is a very special case, because before, in this case, we were talking about, in the other case, we were talking about going to discrete states. In this case, previous, we were talking about what happens when we go from this discrete state K to this discrete state M, where this is from one bound state to another, from bound state to bound state. Discrete, and these are just both discrete levels. But now the new case is we're doing this. We're going from, we have all these bound states here, and we're in this initial state K, but now we're going from the bound state to this continuum state. So there's continuum states, continuum, because there's no discretization in the vacuum. There's no quantization because there's nothing to hold us in. And so as you know, we have free particles, because for free particles, you have a continuum. Free particles, I'm free. And so this is, but we're starting with a bound state. Or I should say we're starting with a discrete state. Let me write it like that. Let me just use that terminology. We're starting with one discrete state. We're starting at one discrete state, but we're having a transition to a continuum. So we're going from discrete state, and these nuances are important, to continuum. Because now it's a little different. Because now in a continuum, you're not going to just one state, but you have to consider the probability of going to many different states. And so what we can say now is we can ask ourselves, what's the probability? What is the probability to ionize the particle? As opposed to a probability to go to a discrete state, we now want to know what's the probability to ionize the particle. And it's different. And so we want to know, so now let's calculate the probability of ionization. Probability to ionize equals what? And this is going to lead to Fermi's golden rule. And so that's the whole point of this, Fermi's golden rule. And it's kind of an interesting and very important result. That's why it's called the golden rule. It's very important. So, okay, so let's calculate it. Let's figure it out. Let's figure out what that probability is. And the whole point that makes it really important is that we're down here in that discrete state. Our initial state is down there, K. And we go up and we want to know the probability to get out. We want to know the probability to go to some arbitrary final energy. But there's a continuum of energies here. And so the probability to escape, to ionize, is going to be the probability to go to all of those states. And so what I have to do is I have all of these different possible final states. I have EF1, and I could have final state 2 and final state 3, final state 4, etc. I have all this infinite number of final states, possible final states, and so the probability to escape is going to be equal. I got to add it all up. I got to add up all the different possible final states. And it's going to be the probability to go to all those different final states. I'll call them C sub F of T squared. I got a sum over all possible final states. So there's a whole bunch of them. Now, okay, so it's going to be so the probability at some time t to escape is going to be the sum of all the possible energies that we can go to, because there's many different energies out there. So I'll write it as this, E sub F. So it'll be C E sub F of T, and I gotta add up all those different final energies. Now, but here's the thing, it's a continuum, and so we have to go. So then, as a result, we have to go from a sum to an integral. And so what we do then is this happens a lot in physics. And so this might, if you've never seen this before, this might seem kind of weird to you, but I'm telling you, this is a sort of a situation that's very common in physics. We often are going into some continuum, some set of continuum states. It's a common thing in physics. And so you have to then you have to convert your sum into an integral. And there's a special way to do it, because the probability to ionize, right here, ionize at some time t is going to be, now to turn the sum into an integral, you have to integrate over all final energies. But now you have to take this probability to go to a particular final energy. But the point is that now there's going to be a number of states, and we have to look at the density of states, because this becomes the density of states. And rho EF, the density of states, is a quantity that tells us the number of states per energy. And it's a thing, you know, there is a number of states per energy, and it depends on the energy. At higher energy, there's more states. At lower energy, there's fewer states, and we'll actually calculate that at some point, so you can see explicitly what I mean. But the important thing is to know is the definition, which is that the number of states in the interval what's the best way to write this? If I have some energy, and this is EF, and this is EF plus DE, and if there's a continuum of states everywhere, continuum, then the number of states in this interval is going to be where E is less than or equal to EF, or greater than or equal to EF, or less than or equal to EF plus DE, then the number of states in the interval, in that interval, is equal to rho of EF DE. So that's really the definition of the density of states. The number of states in that interval is rho EF D times DE. And so that is the definition. This is the actual rigorous definition of the density of states. And that's what we need in order to do a sum over a continuum number of states. So it's a very important concept. So if you've never seen it before, then this is, you might have to sort of spend a little time trying to wrap your mind around this concept. Okay, so that means then that we use it, and so now we can write our integral using this new density of states concept. And so we have to integrate this transition probability over all possible final states. And so we'll just plug it in. And so it's not that hard, actually. You just plug it in. So we can see then that P of T, the probability at time T, is going to equal, it's going to be this thing. It's going to be all possible final states times the probability C, which is now a function of EF and T. I used to make that a subscript, but now it's a function because we're going to make energy a function now, a variable, a continuum, continuous variable. So this is my probability of ionization. And so we're rho of E equals number of states per energy equals density of states. And sometimes we just call it DOS, density of states, DOS. That's actually common usage, DOS. And so then we just plug it in. We have a formula for this because we know that the formula for that, and so we can then just write out this integral. It's the sum over all EF, all possible EF, and we have that formula, and we know the formula is just going to be the matrix element that links the initial state to the final state squared by the perturbation times sine squared EF minus EK minus H bar omega times T over 2H bar. And then this becomes EF minus EK plus H bar omega squared. Where this is, and then I have to multiply times the density of states times DEF. Okay, so, and that's because this thing, we know what this is, this probability for the harmonic perturbation. Because that's what we had derived before. This result for the harmonic perturbation is this. Okay, so that's the integral then that we have to do to figure out the probability of ionization. We have to simply do that integral. But now there's a trick that we're going to do, which is essentially a math trick. Because what we're going to do is we're going to realize that this function, remember if I did this function C m of t squared, remember it looked like this, where this was h bar omega and this was delta E. And so we see that what's going to happen is, if I'm sitting here in some initial state, K, then we can see that if I jump up to some final state, EF, then there's going to be a probability that the function, if I plot it, it's going to look like this. It's going to look like this. And so there's going to be all these states everywhere, but in the integral is this function. It's the same function, and it looks like this. And so what that means is, because this is, if this is my final state, you can see that this function is going to be where this, if this distance is h bar omega, then you can see that as soon as my delta E deviates from h bar omega, the function gets really small. And that's what I want you to see. So I hope you see that. So so that means that as I start going out in that direction, the factor gets small. And as I go in this direction, it gets small. And so the bottom line is that delta E really wants to be h bar omega. That, and so that's really where you have the highest probability to have an excitation is at h bar omega because of that peaked function. And so I could just say that, you know, delta E wants is most likely to be h bar omega. And the reason why that's important is because this simplifies, it simplifies the integral. Because now what I can do is, these two factors that depend on the final energy, I have the density of states and the matrix element. And those depend on energy. I mean, you know, because if I have these, because remember that the density of states depends on the final energy, and the matrix element, H prime final K, that's going to be the final state, which depends on the final energy. And then that's going to be, you know, H prime, and then the initial state. And so you can see that this state depends on the energy, the final energy, my final state. And so rho EF and H prime of FK are energy dependent. But if my integral is strongly peaked at a final energy of h bar omega, then that means that those expressions simplify, because if integral, or I should say the integrand, is peaked at delta E is equal to h bar omega, then we only need to calculate, then we can say that rho of EF is approximately equal to rho at K, the initial, plus h bar omega. And I could, by the same token, I can say that the for h prime of fk, that's going to be equal to simply the final state, where this is final state is going to be at the energy of the initial state plus h bar omega. So it's one part. So I only have to worry about one particular energy for calculating that matrix element, h prime phi k. So it simplifies them. So that's going to be just one. So what that means is then is that they're not energy dependent anymore. So I can pull them out of the integral. I can pull these factors out of the integral. And so that means then that my integral is now going to be look like this. So my P of t is now going to look like this. Rho density of states gets pulled out. It'll be evaluated at the initial state energy plus h bar omega, and I can pull my matrix element out because it's evaluated only at one energy, and then I have my integral for all possible final states, and the possible final states are going to be but I still have this. But this part is still complicated. I still need to keep all the details inside of the integral, this sine function. I haven't simplified this yet, but I will. All over f minus k minus h bar omega squared f. And then, okay, so that's what my integral looks like. And then we notice, then also I want you to see that here in this integral, you see, normally I want, for the final states, I would just be, we would have to think of all final states. We'd have to be careful about all the final states, but now we can just do this integral from negative infinity to positive infinity. And the reason, and because normally you see it doesn't really go to negative infinity. You know, this is, you know, E equals 0, and then this is the negative energy spectrum, and this is the positive energy spectrum going up. And you see that it's discrete in the negative energy, and normally there'd be some complexity in this energy spectrum, and it doesn't really notice that this is not infinity. This is just the bottom of the well, V naught, whatever it is. I mean, normally but we don't have to worry about that because this integrand goes to 0 pretty quickly. And so even if we have this go to negative infinity, it doesn't matter because the integrand goes to 0. And so as we get farther away from h bar omega, it just goes to 0. So it just makes the integral easier. So it's just a math trick. That we can make this integral symmetric, and it doesn't change the value. Okay, so now we got to do this integral. And to do the integral, we're going to do another math trick. We can do this integral by doing a change of variables. A change of variables. And it's a cute little math trick. What we can do is we can say, let's let U equal EF minus EK minus h bar omega t over 2h bar. And then what's going to happen is we'll then have, you can then see that I'm going to have EF. There's a couple of things to notice. First, you can notice that if I take a du, then I can have du is equal to, and all these guys don't change, so they all go to 0, but it's going to end up being t over 2h bar t times dEF. And so then we see that dEF is equal to 2h bar over t du. Okay, so let's just change the variables, algebra, to h bar. Okay, and so, and then similarly, we can solve for this variable, EF minus EK minus h bar omega is equal to 2h bar over t times u. And so then if I square it, then I square this too. Okay, so then, so what I can do then is I can plug this right there, and I can plug this right there. And I can plug this right there. And so that simplifies my integral. And so now I can see that my integral becomes a much nicer thing than it was before. My integral becomes rho of EK plus h bar omega times h prime fk matrix element squared now times the integral negative infinity to infinity of sine squared u over 4h bar squared over t squared u squared times 2h bar over t du. All right, I'm just plugging in all my changes of variables. And so then it becomes this, so then I get this very cute result, which is that the probability as a function of time is equal to rho, my density of states at the final energy, times my matrix element connecting my initial and final state, times t over 2h bar times this integral negative infinity to infinity of sine squared u over u squared du. And it turns out that this is a famous integral. You can look it up in a book. And it equals none other than our old friend pi, a piece of pi. That's what it is. It's a piece of pi. Yay, pi. Okay, so that's pi. And so that means then that the final integral, we have our answer. It's equal to density of states plus h bar omega, matrix element squared, connecting the initial and final state, times pi over 2h bar. We've got this pi factor, and then there's time. It's linear in time. And so that's really interesting. It's linear in time. And so that means that the probability, so this is the answer. I mean, we calculated it, but there's still going to be one thing more that we're going to do. But I want you to sort of think about this, because I know that when you first see this for the first time, it's kind of strange, because you're thinking, well, why is the probability linear in time? And so you see that the probability, so we have to ask ourselves what this means. And so what it means is that, you know, you have to remember what the situation is. We start with all of our amplitude, all of our green goo, all there in the state K. And so initially, Ck of t equals 0 is 1. The probability to be in that state is 1. And what we're doing is we're asking ourselves, what's the probability to go out here, some energy h bar omega above? And so I have my probability here. That's my p of e final of t. And the point is that this probability is growing with time. this is growing linearly with time, growing linearly with time. So the way to think about it is that the probability is flowing out. The probability is flowing from this one state into these continuum states. It's flowing in that direction, the probability. And so it's sort of like saying that I have my initial state where at t equals 0, all of my probability of probability equals 1 is in my initial state, and my final state has no probability. There's no probability here, that's 0. Whereas as t gets bigger, let's say t equals t naught, then what happens is I lose some of my probability. So now I lose this much. Let's call that delta. And so I have 1 minus delta left. And in this final state, I have the delta. And then this is the probability. That I'm talking about. And so now if I go to t equals 2t naught, then you can see that the probability becomes twice. I lose twice as much, 2 delta, 1 minus 2 delta. And here I'm going to have, now I have 2 delta. It's increasing linearly in time, etc. You know, and then at t equals 3t naught, it'll be 3 delta, and I have 1 minus 3 delta. So I'm losing it linearly and I'm gaining it here. 3 delta. So I just want you to sort of, I want you to visualize a flow of probability from the initial state to the final state. And so that means that and so the final state is gaining probability at a rate, at a certain rate. So at the rate, for example, it's going to be the rate delta per t naught. So I want you to feel comfortable with this concept of rate. So I have a rate, because in physics, this concept of a probability rate is very important. So it's a probability rate, because I'm moving probability over to the final state at some rate. So the rate is equal to the probability per time. Okay, and so what that means then is that here, notice my probability is changing linearly, and so the probability rate is just P of t divided by t. Because if my probability is just changing linearly in time, if I divide it by time, then I get the rate. And so that's telling me how fast the probability is moving equals how fast probability is switching over. And so then we can just plug into our formula, and we see that we have P of t over t is equal to the transition. So we call this the transition rate. So that's an important definition, is equal to rho of ek plus h bar omega times the matrix element that's connecting the final and initial states through the perturbation times pi over 2h bar. And this is Fermi's golden rule. Fermi's golden rule. All right. And it gets a little star. And that's Fermi's golden rule. And the important thing is that the way that everyone remembers it out in the real world is that the transition rate, the rate at which you have transitions, is always going to be proportional to a matrix element squared times a density of states. I'll just call it DOS, density of states. All right, and this is when we have a transit. This is for a transition from a discrete state to a continuum, which happens all the time. Like, for example, in radiation, it happens all the time because you have, say, a proton or neutron stuck in some nucleus and it escapes, bing, and that's what radiation is. That's radiation. And so, you know, Fermi's golden rule comes into play because you're escaping. You're going from a discrete interior state into the continuum free states. So it's a common thing in physics, happens all the time. Okay, and I think that's where I'll stop because I know I've gone a few minutes over, so this is a good place to stop. So bye-bye, see you later.